Whoa, is that new? What is that noise? Okay. Oh, Isabel. Nice. Okay. All right. Welcome everybody. We are going to get started. This is the first kind of recap of our first Art and Tech project. So we're very excited. I'm going to present, and Jay and Michael are going to be discussing everything, what we did and how it all works. So let's get going. Oops. Okay. All right, Jay, why don't you start?
All right. Hello, everyone. Today, Michael and I are going to talk about the first Art and Tech project we created. So my name is Jay, and I'm the director of Art and Tech. I'm a rising sophomore at Saratoga High School. I've been at Hongyun Art for about 4 years, and I've gotten several clarinet awards. I like to code, and I'm terrible with hardware design.
Nice. Honest.
So a little about myself. Hi, I'm Michael Song, and I'm Art and Tech Team Director. I've been with Hongyun Art for 4 years now. I was part of a GI trip back in 2019. I was supposed to go on a GI 2020 trip last year. I'm an upcoming sophomore at Cupertino High School, and in my free time, I like to build and make things. And I'm a terrible coder, so it kind of gives me a headache.
All right, so we led this project from the beginning of last summer in 2020 with a group of team members. During this presentation, Michael and I will describe our own focused area during the project. This slide shows the work done by Daniel Rosen, which inspired us to choose our mirror project. Here's the link to a YouTube video showing his work.
Okay, so I'm going to show you a little bit about this.
Daniel Rosen has spent a lot of his career building what he calls mirrors, but they're not what you think.
My work centers around the idea of participation, of interaction, where the viewer becomes a part of the piece. When a person stands in front of one of my art pieces, they immediately understand the interface to it. They will see themselves reflected. There's no learning curve. There's no question about what is the contents of the piece. The contents of the piece is you.
Rosen's made mirrors from wooden tiles, trash, fans, even pom-poms, each meticulously designed, built, and programmed to reflect the viewer's form.
I remember getting the idea that I could create a mechanical display by taking anything and just tilting it up and down towards or away from the light. Just like maybe my hand is doing right now. It is bright when it tilts up. It is dark when it tilts down.
Daniel Rosen has...
All right.
All right, so for us, his work didn't provide much technical information as to how it was implemented. So we have to design our project from scratch.
Throughout this project, there were many responsible for seeing this project into fruition. I worked on the hardware side while Jay worked on the software side. There were plenty of individuals who helped us throughout the journey. We'd like to thank Shreyas for helping us with camera detection and coding, and helping us calibrate the units. And we would like to thank Grace, Annie, Alexandra, Angelica for assembling the majority of the mirror units. And I would like to thank Robert and Eric for helping us with the wires, and many more that helped us see this project come to fruition.
All right, overall process. So here you can see the overall process we took from the beginning of the project to the end. Our goal was to have 100 mirrors in a 10 by 10 grid. The very first step was to prototype a single unit that can be plugged in. There were a few iterations of prototyping to finalize the design. We will talk more about those details later. The second step was to build the whole 100 units using the unit design from the previous step. The third step was to develop a program to detect objects from a camera, which will then send signals to each unit to change the behavior based on the result of its detection. The fourth step was to perform the integration of the entire 100 units by connecting them to controllers and the Raspberry Pi so that we could run a software program to control their actions altogether. And finally, the final step was to complete our tests and fix any issues we discovered. There were many challenges for every stage, but that we didn't anticipate, but we overcame them by trying several times and fixing any errors we encountered. We will elaborate more on this as well.
This project required a lot of prototype and testing. For one, there were no publicly available resources related to mechanical mirrors when we first started. So I have to create everything ourselves, which is one of the leading factors of why this project took so long. In total, we had 4 main iterations of our mirror units. So the first prototype was a proof of concept, so obviously it was pretty rough. We decided to use sample paint cards because they were widely available and free, and who doesn't like free stuff? And it offers some reflectiveness, and they were directly mounted to the motor. This poses many issues, however. First, the paint cards were extremely bendy and not very rigid. They were also rectangular, which made it a lot harder to work with and make it look nice. Our test with the material gave us far from stellar results because they were ineffective at catching light and casting shadows. And obviously, walking out of your local Home Depot stuffed with paint cards is a tiny bit suspicious. Our mounting design also posed an issue as the radius between the motor and the card was extremely large, that the whole card would hit the units mounted above and below as demonstrated by the diagram at the right. For prototype 2, we implemented mirrors that were cut to precise dimensions instead of the paint cards. They offered both rigidity and reflectiveness, and we used a linkage in between the motor and the mirror made with paper clips, as shown in blue in the diagram. Solving the previous issue of having a large radius when turning, by shifting the point of pivot closer to the center of the mirror, it allowed the mirror to closely pivot around itself, reducing the radius demonstrated by the diagram to the right. Additionally, the servo motor is glued into place. However, this also produced its own issues. For one, the mirror was extremely reflective and therefore did not cast even lighting and shadows. The prototype implemented straws, popsicles, and dowels for the pivot design, which was not very sturdy and obviously had to go in our next prototype. However, the dowel rod did stay because it provided a nice pivoting surface. Moreover, we had to choose what motor we wanted. We chose servos over steppers, despite steppers having higher power and precision. Servos were chosen because of their cheap nature, small footprint, and light energy usage, making them much easier to power with external power supplies. We had to pick from one of the 2 servo motors shown on the top and middle of the slide. We chose the middle one because it offered attachments which were necessary for our pivot design, mainly the servo arms required to link the wire and the motor. For prototype 3, we swapped to a completely laser cut plywood build, and the servo was taped in hopes of not damaging it. Challenges persisted as the rectangular footprint of the plywood box was a headache to work with, and mounting and taping the servo soon proved to be a terrible design as the tape would delaminate itself. Prototype 4, we implemented an outer shell in order to make the footprint of the units into squares, therefore easier to mount side by side. Each unit is around 4¼ inch by 4¼ inch. Cutout were made in the outer shell to accommodate easy cable routing, and now the servo is glued in, and once again, we have gone full circle. But we soon realized that these additional pieces did not only take more time and material to produce, but also more prone to breaking, and had uneven tolerances and would cause minor misalignments. This issue was extremely minor in our handful of test units, but it was extremely common once we had to ramp up production. 100 units was not a small feat. It was mounted to a 4 feet by 4 feet plywood board. Each unit was spaced out slightly because of the uneven tolerances mentioned earlier. If we were to directly glue the units together, making it seamless is virtually impossible. Holes were drilled between every 2 units for cable routing, which proved to be a significant oversight, as it was time-consuming to find which cable led to which motor. And it was like fishing a thread through a needle, only now you had to do 100 times. The outer shells were glued in while the inner units were press-fitted in, and this took a lot of finessing because of the weird tolerances.
All right, calibration. So this is one of the biggest challenges we faced during the project. Initially, we divided our team to build 100 mirror units, but we realized that they didn't behave the same way when we tested the angles. The right top video shows each unit turning at different angles, even though we set the same angle in the code. So we reworked over half of the units by calibrating them or resetting the angles in the servo motors to the same angle such as 180 degrees. As a result, you can see in the bottom right video that multiple units are working with the same angles after the calibration.
Okay, next slide, right, Jay?
Yeah. All right, coding. So when I first started coding, I used Java because I was more comfortable in that area. As I coded more, and I also tried to understand the OpenCV library, which supported the image processing for a camera. Then I realized that the servo controller library was a Python library, so I switched to Python to make a program by using the Java code I already created. Some of the things I had to think about was grayscaling an image for the camera, its detections, and how the pixels will be represented as images. Using the OpenCV library, I was able to use pixels from the image and grayscaled it in order to reduce the image size to 10 by 10 pixels, since that was the size of our board. The image on the right, or the video on the right, shows how the objects are recognized after all the translations happen. We tested the functionality independently without using the motors and then applied it to the motors afterwards. In the final testing round, I also made two fun programs that executed a nice domino effect as well as a spiral.
Wiring was not fun to say the least. We originally planned to use only 7 boards since each board can control 16 motors, which fit our requirements for 100. However, we soon found it to be easier to use 10 as we're able to distinguish each row, meaning I had to solder 10 boards, which was the most excruciating thing I've done in this project. We also used jumper wires to link the board to the motor, and since each jumper wire is 1 by 1, I decided to heat shrink them into 4 by 3 connectors or 2 by 3 connectors, depending on the setup, making them larger connectors and therefore easier to plug and unplug, shown in the picture in the middle. We also taped each exposed connection so they would not unplug under tension. We originally used blue masking tape, however, they were easily unwrapped, and we had to upgrade to the more appropriate electrical tape. The servo controllers we used were supposed to be able to stack on top of each other. However, it soon created a leaning tower of pizza, and it was terrible for the connectors. And the 100 cables coming out of it made it kind of a hot fire hazard. So we had to add 2 by 20 extension cables between 2 boards.
All right, how it works. So this diagram is basically a brief summary of how all the components work together. The Raspberry Pi connected to 10 Adafruit servo controllers, where each controller connected to 10 more servo motors, and each controller corresponded to 1 row. The Python code was deployed and executed on the Raspberry Pi. And so the code read the image data from the camera and did some transformations to map it as 10 by 10 pixels. After that, it sent the angle for the motor corresponding to each pixel. And now Tommy will show the video.
Cool.
skip to the next one.
Yeah. Woohoo! Yeah! Woo!
All right. So I'll take over now. First of all, I want to say good job to everybody for helping on this. It was an extremely long project. I know because we didn't really think about like how long. We thought, oh, this should take them, you know, maybe a few weeks to do in the summer, and we'd have like the prototype done, and it'd be great. So of course we were wrong. It basically took them up until the end of, I'd say about April, I think, close to April, maybe early May to get this done. So they just literally finished this. And it was quite a slog, especially for Michael and Jay, who came pretty much every week, stuck it out, and just kind of get it done. Definitely applaud these two guys for spending the entire year basically working on this. You guys did a phenomenal job, unbelievable. Also, thanks to Shreyas and Grace and the whole gang for helping out when they could to kind of get this put together. Very, very huge team effort. So fundamentally, why are we doing this, right? That's kind of the questions, like why do you want to build this thing? And this sort of drives home our point, like Hongyun's like fundamental understanding of art is that it's not just about pretty pictures. So Hongyun and I have basically traveled the world to validate this truth. So I'll show you some of the things that we've seen, and then we can go over what we're going to be doing next. Okay, so give me a second. I'm going to switch to some more YouTube's fun. So this is at the Singapore Art and Science Museum. So our one of our friends called Team Lab, they are a giant art collective in Japan, and they do cool stuff like this. So what you're looking at is basically a lot of LEDs, large addressable strands of LEDs, just arrayed in, you know, top, like hanging down from a ceiling, and they just create patterns in it. So, I mean, it's basically like technology that you can use to light your kitchen or your house, but they just took it to an insane, you know, logic, like sort of insane extreme, right? And it produces kind of a very beautiful effect. So this is a demonstration where like the person experiencing this art can send patterns to the array, and it'll kind of do this whole dance of light around you. So it's quite beautiful, and it's to me it's art, right? But it's a melding of art and technology together. Okay. So let's see the other part. Yeah, so this is in the Marina Bay Sands across from the Art and Science Museum. So this is, again, another LED array and a giant screen that you can walk on underneath. Both of them are reacting to you as you walk around. So you see as this person walks around, there's like stuff growing out of your feet, and it's very beautiful. And it's all fundamentally, it's just different technology parts put together. So me being an engineer kind of said, oh, this is, I mean, it's difficult in that it's big and it's a lot of things, but technically speaking, I knew that our students can do this. I knew that they have the capability to do this.
So 2018 summer, we brought our GEI team go to visit this place.
Yeah, we took our students to go visit this, and they were like amazed and kind of blown away by all this stuff. So
Yeah.
very interesting. So we, we talked to Team Lab, and they invited us to go check out their studio.
The headquarters in Tokyo.
Right. So we took, I think, one of the GI teams. I forget which year.
2017.
2017.
We were
summer.
invited. Yeah.
So we took them to visit the Team Lab headquarters. They took us into their lab, and they kind of explained how their whole process worked. They said they have a lab of engineers who develop units of coolness, right? So they have like guys who make mirrors that move, and guys who make water shooting and LED strands and how to address them, and all these sorts of like interesting unit parts that they can put together. And then they have artists and project managers that kind of put these things and put them together to make an artistic piece. So we thought, hey, that's something we have a lot of capability for in our hometown.
Your Bay Area.
In the Bay Area, we have a lot of techie kids and people, and we have a lot of artists, and we're like, this is fundamentally something that we could do. So ever since then, I've been trying to figure out like, how do we do this? How do we do this? Back in 2017, we didn't really have the space for this, right? We had Hongyun Art 2.0, if some of you remember. It was a pretty small space, and then by the time we moved out in mid 2019, it was kind of packed to the gills. So we didn't really have the space for this. So now that we have it, we are taking advantage of it, and this is kind of the fruit of that. Hongyun and I have also traveled to a couple other places, Venice, Italy. So Venice, Italy has the Biennale di Arte. It's like it's a big art show every 2 years. It's a contemporary art show, so that means like modern art. And all that you really see there are these large pieces, some of them very interactive, like what Jay and Michael and the team have built. And that's, to us, it's like, that's the future, right? This is where art is now, and this is where it's going. So if you guys want to experience something like this right now, there's in San Francisco, it's called Van Gogh SF. Fundamentally, it's just a big giant auditorium with Van Gogh paintings that move around and do cool stuff. It's just a lot of projectors in a dark room, a lot of music and all that kind of stuff. But it's really cool. I encourage you, if you're feeling like you want to get out of the house, you want to go see it, go check that out. There's another thing called Meow Wolf. It's got a funny name, but this is a very contemporary art type of thing. It was born in Santa Fe, New Mexico, and it's coming to Las Vegas. It's basically like giant rooms that they let artists do whatever they want. So there's a lot of lights and a lot of things that move around, and it's a really cool melding of art and technology. So to us, to me at least, this is where art is going, right? This is art, what art currently is. Okay. Yeah, so you can see like these are some of the things that are very interesting. I'll show you a couple more videos in a little bit. So the overall goals with Art and Tech, of course, is to have fun, especially with technology and art. It's to learn something new. I'm sure Jay and everybody and Michael and everybody who's working with this, they've definitely learned something new, not only technically, but about your capabilities and yourself, right? Like this is a huge project. I challenge anybody, if you think you can make this thing, try it. It's extremely hard. These guys worked so hard on this. I kid you not, it's an absolute monumental challenge to do this while you're in high school, while you're going through school, while you're taking art classes, while you're taking clarinet and whatever other classes you take. This is extremely hard, and they did it. It's awesome. And this is fundamentally the goal of this thing is to create something novel, something interesting and fun for everybody to enjoy. So my goal was to put this thing in somewhere in the front of the school so the little kids, parents, everybody can come take a look at it and play with it and enjoy it. Okay. And also to make this kind of full circle, our final goal is for these guys to be able, or for the team members of this to be able to create their project, show it to everybody else, and also to teach other people. That's the key part for us, is that you can take what you've learned, teach it to somebody else, and this becomes kind of a thing that you can help other people with. Like, there's underprivileged kids all over the place. And our belief is that if you can give them some sort of fun way to approach technology, then maybe you might turn the lives around for other people, right? They might be like, wow, this is really cool. I want to learn how to do this full time. I want to be, a computer engineer. I want to be a hardware engineer. I want to be a designer, all this kind of stuff. So it's something that I feel is not only fun for us to do, but can affect our community all around us. So that's the next phase of this. So that's where we're going with this. Okay. So let's talk about what we learned from this iteration. So number one, we have to consider the feasibility of the project. So this was sort of definitely underestimated by me and everybody else. We just sort of dove into it. We didn't know how long it was going to take, all that kind of stuff. Like I said, this was a monumental project, even for like a team of engineers to do. It would have taken them many, many like months if they worked on it, full time. It's a lot of work. So we needed, definitely we needed time commitment from team members. So like everybody sort of came when they could, and there was like mismatching schedules and things sort of were kind of haphazard for most of the project. I think that contributed to kind of how long it took. I think if everybody had like, like a free block of time for like a few weeks, we could have gotten really fast, really far, really fast. Communication was a little bit lacking. I noticed like we'd chat on the Slack and nobody would answer. So there's definitely issues there that we have to work on and make sure the team is aware of. Definitely what helped a lot was Jay's dad was a proctor. So he helped support the team because I'm, always running around with helping to run the school and everything. So it's very hard for me to help to jump in, even though I'm an engineer. Definitely having a parent proctor, I think, was a key component in pushing this whole thing forward and keeping it going. So awesome job to Jay's dad. Love the sort of support, and it's something that we will make a part of this project. We need to have small teams of 3 to 5 people who have time and who can meet. So that's the key to do this. If we have too many people, it was kind of hard to manage everybody and getting everybody there. So if we had like a smaller team that just kept coming and at the same time, so it would be good. I also noted that we need various roles, so not just hardware and software like these guys and the people who helped out, but we also need like project managers, finance people. So you don't have to be technical to join this, right? If you want to help project manager, that's actually a lot easier. It's just a lot of like running around finding things for people that they need. Hey, we're missing this thing. I need to get this guy, this person here.
Need a lot of communication.
Communication skills, right? Yeah. Finance is also like managing money. Like, hey, here's the budget, and oh man, we need this part. It's too expensive. Let's find a creative way to solve that problem. Again, the proctor, having an adult in the room is very important. And then we need outreach people who can reach out to other organizations to find partners that our students can help teach this to. And to maybe gain funding and that kind of stuff. So, yep. So probably there may be an overall management team. If we have a bunch of these small teams of hardware, software people that kind of build their projects, we might have a single team that manages them. I'm not sure how we structure that yet, but we'll work on that. Okay, so let me show you some project ideas. These are not like set in stone. These are just kind of things to kind of get everybody's mind thinking about where we can go next, okay? So this is called the flower garden. So let's see.
Floating flower garden needs a gardens using over 2,300 year living orchid flowers. Orchid doesn't need to have its soil. So it's there still alive in this garden. When the viewer opens the door, you feel you cannot enter because of the filled up the rooms. But when you step inside, the flower in front of you going up, this garden is connected on the networks with vegetation, and it's always making dome around you. If there is 2 people and it's walking 2 domes and meet up inside the garden, it's become bigger dome. So there is no border between its base and its an object.
So that's one idea. I really like this idea, fundamentally because each unit, I believe, is relatively small and feasible, but we can talk about that. This is a different thing. This has pretty much no hardware. I mean, there's projectors and stuff involved, but there's no like hardware design involved.
light up a city, like a city hall.
So I mean, what you're looking at is a bunch of high-powered projectors and then animations projected onto the high-powered projectors. And oh, this is Singapore. And the idea is you take into account the shape of the building and then use that as part of your projection. So this is another project that I'm thinking might be fun. This is generative art. So this isn't really like rendered art. It's just an algorithm that produces
It's easy to get lost in Rafik
produces
Anadol's
these
surreal
images.
installations.
Yeah, in
But
Las
dig a little
Vegas.
deeper, and you
Yeah.
realize his work is
Yes.
made up of millions of tiny pieces, and that every single little point represents a piece of data that he's fed through a neural network to show us his vision, our future.
I was always like trying to like speculate this idea of can data become a pigment. At the end, the data is truly numbers that has no kind of any scheme or skeleton. But what I'm trying to as an artist is find an algorithm that can narrate the moment of data, kind of like make an invisible moment visible.
Enormous data sets inspire most of Anadol's art, and he uses machine intelligence and algorithms to create visualizations, what he calls data sculptures, like this piece called Machine Hallucinations. He started by finding 113 million images of New York online
and let the machine learn from this entire corpus of data. And then we also find a way to erase the humans from this data and only focus on the buildings, nature, and environments that is a collective memory of New York.
Once all of the images of people were removed, Anadol was left with 10 million pictures of New York. He fed them through a machine learning
Wow.
algorithm that generates visual associations as it learns.
Cool. That's very cool. Let's see, I have a couple more. This is the mirror project that these guys built this year, but this is like the mirror project on steroids. So I'll show you what this is. Okay, and I think this is the last one, yeah. So this one's actually a bit simpler. It just looks complex because of the shapes, but fundamentally simple. All right, so as you can see, it's okay. Yeah, so and these are not the only ideas, right? These are just things to kind of bounce around in everybody's mind and think about it. If you don't know what you want to build or create, that's fine. You know, the goal for people is to get together in a group, talk about it, and then see what is feasible and what you want to do, right? And then, you know, there are things maybe you need to learn. That's totally fine. So the next steps, I'd like, if you want to do this next year with us, just go to this link, hyafound.org/signup. By next week or this Sunday. So there's a donation that we're going to request. Fundamentally, that money just goes to buy supplies for your team. So if you need like mirrors and motors and Raspberry Pis, that can be, you know, added to the budget for your team. So the iterations are going to look like this. So we have summer, you're going to meet your team. You're going to figure out a project to make. Figure out some schedule to meet regularly, make a prototype and test it, right? So that's the goal over the summer. Fall is you're going to build it in scale. So you're going to build like, once you have your prototype working, you're going to build either a lot of them or make it bigger or whatever it is that your project is. And we're going to put it into the studio and we're going to let others come play with it and see it. So they're going to help you test it, right? We're also going to have our outreach team begin reaching out to potential partners to see if we can introduce our project and help teach it to others, you know, like YMCA or other schools. And in the spring, we're going to hold the workshops to teach others and so how to make a small scale version of your project. So they're not going to make like a gigantic version, but you can teach them how to make like one unit. Like, you know, if you had like this mirror project, for example, you would teach them to make one mirror, and then maybe you can tell them like, well, if you want to build a whole bunch of them, we can kind of coach you. But now that you have one, you have the building block to build more and more of them, right? Let's see. All right, that's it. Anybody have any questions? I don't know how I'm going to see you. Hang on a second.
Maybe the message.
If you have a question, you can pull up the chat. Oh, let me see. Somebody's got a chat. So somebody asked, what is the expectation from the students and what is facilitated by Hongyun? Right. So the expectations from the students fundamentally are just having the time and work ethic to come regularly and work on your project, right? So it's not like we're asking a lot of you. You will be learning, you will be trying to figure things out. I will, like me personally, I'll try to point you in the right direction, but like I said, I can't be like individually covering every single team and trying to work on it with you like day in, day out. That's not the goal of this. If you run into roadblocks, that's what we're here for, to try to help you get over those roadblocks. But most of the time, you and your team will be working together to kind of figure this out.
And the Jay and Michael can help.
Yeah, Jay and Michael hopefully will stick around for iteration 2. Sounds like they're excited. I'm hoping to continue, try a different project maybe. And then they can be helpful in sort of answering questions and leading and guiding as well. Any other questions? Thank you for your presentation. Oh, thank you. You're welcome.
Amy.
Any other questions? So I think fundamentally, like it's not a class. Like we're not leading you through building a project. Like Michael was saying, like if you saw how Michael like went through this whole like prototyping thing, he basically was an engineer. Like he designed like those units from the ground up, trying something, he learned something from it, built prototype 2, tried it, built prototype 3, tried it, found some problems, built prototype 4, right? Even like prototype 4, it's functional and it's relatively stable, but I'm sure like he has ideas on how he can improve it, things like that, right? So that's fundamentally what the goal of the project is, to kind of get you in that mindset of, I'm building this thing, I'm kind of searching and trying to grow my own knowledge and experience. Okay, so this isn't a class, so to speak, where we're going to teach you how to code like hello world and all that kind of stuff. This is not what we're doing. If that's what you're looking for, this is fundamentally not the right venue for that. So. I don't know. Anybody else? Does anybody have anything to add? Michael, Jay? No, you guys good? Jay's dad? Nothing? I don't know. Good. I think we're good. Okay. Any other questions, you guys? Anything? No? All right. So we'll be posting this video on the sign up site and then sending out emails and everything so people can go get reminded to sign up. Hopefully some of you will join us and we can hopefully get at least one group of 3 to 5 students, maybe 2 groups. I'm hoping that'd be fun to have 2 different groups kind of making completely different projects. You're not competing, okay? You're friends. You're working on different things that will turn out to be hopefully both awesome and wonderful for people to play with. All right. The mirror project, what we're planning to do is we're kind of stabilizing right now because there's all these wires and stuff still everywhere. We will put it out in the beginning of fall for people to play with. We don't want to leave it out in the summertime because we have a lot of little kids coming in for summer camp. So, I don't like, we're going to block the purple room where the mirror lives right now. We're not going to let any of the little kids go in there for the summer. But hopefully in the fall, early fall, once summer camp's finished, everybody can come and check it out and play with it. And, hopefully it'll be hopefully a lot of fun. Anything else? Anything to add? All right. So I want to thank everybody. Thank you, Michael, Jay, everybody for who jumped in and helped out. Definitely appreciate all of your help and effort to get us here. It's super huge accomplishment. Once again, completely blown away by what you guys have made. It's super, super cool. And I'm excited to see iteration 2 and what we can come out with. All right, guys. Thank you so much.
Thank you.
Thanks.